Swayam Prabha. Digital India. Educated India.
As usual, I got good questions during the break. So one that I want to bring your attention to in particular. So when we talk about phase field and elastoplastic fracture, we discussed that we have something like where the driving force becomes, it could be the elastic one plus some fraction of the plastic one. And we think that based on those Taylor and Quinney experiments, this should be 0.1, so 10% of the plastic work. I mean, again, up for debate, but I think this is the most consistent one. So some people ask me how to compute this one. So you can do it always in an incremental way. So you can always compute for every increment, the dot product of the tensors. But there's also, of course, analytical solutions. So in this case here, this is a recent paper where we discuss about implementing in COMSOL facial fracture for hydrogen embrittlement. But you can see that for this given kind of hardening law, power law hardening law, that is very typical. So this is flow stress, initial yield stress. This is the yield strain, so sigma yield stress divided by Young's modulus. And this is strain hardening exponent. Then you can have an analytical expression. You can derive an analytical expression for this. So yeah, I mean, this is a very typical hardening law behavior that you normally do. If you are dealing with linear hardening, it's even easier. So yeah, I just wanted to say that there are some expressions out there if you are in the process of implementing those things. And I think that we have uploaded the code for this one as well, so you can take a look and always find it in the code if you need it. Okay, so we are done with fatigue. And we start with the first session of hydrogen embrittlement, to be continued tomorrow. Let's see how far we get. So I have two sets of slides. I wasn't sure where to cut them. So we'll see how far we get, and we can always continue tomorrow. So I believe that you were all, I saw a lot of you in the seminar. I couldn't keep track of everyone there, but I think all of you were there, or most of you. So I'll try not to repeat the same information, but I'll try to provide complementary information. And just in case some of you couldn't be there for whatever reason, I'll try to maybe emphasize some of the key points. It will be a reminder of the key points for everyone else, and introduction of the key points. But again, this is the lecture 6. And just a reminder, what we have left is 2 sessions now on hydrogen embrittlement. I know some of you work on this, also from an experimental point of view. So I want to discuss a little bit the physics of this interesting problem. So we'll be looking not only to the modeling, but a little bit on the metallurgy and understanding. Then tomorrow I will continue to discuss hydrogen embrittlement until we run out of time, and then I'll move into multiphysics. How you treat any multiphysics problem. And I will do examples with hydraulic fracture, stress-assisted corrosion, thermomechanical fracture. But in general, I'll provide a framework and a way of implementing things for you to implement any other multiphysics problem that you're interested in. And then on the last day, I'll discuss corrosion and batteries. Okay, so hydrogen, you heard yesterday the motivation. I mean, it has always been a big problem, but it has traditionally been a problem for high-strength materials. I'll tell you why now. Or traditionally been a problem in very aggressive environments like oil and gas. So yesterday we discussed why now it's becoming a more pressing problem, why the hydrogen community has gone from conferences of 100 people to conferences of thousands of people. And this is mostly due to the need to use hydrogen to decarbonize applications. And I think in general, the engineers have done a great job in decarbonizing applications. I think tomorrow I will tell you a little bit of the motivation of multiphysics problems based on what the engineers have achieved in terms of reducing the energy cost of solar panels or wind energy. But I think it's fair to say as well that we have solved kind of the easier problems to solve. Now we need to decarbonize many applications and sectors that are very difficult to decarbonize. One of them is aviation. You can imagine, I mean, how do you decarbonize aviation? So there are not many options. The batteries, if you needed a battery, if you need to have an electrical plane with a battery to travel from New York to London, you'll need a battery on the size of the Earth, of the planet Earth, so no chance you can do that. With sustainable aviation fuels, if you wanted to replace every plane out there with sustainable aviation fuels, you need to dedicate to this sustainable aviation fuels a size of land that would be 2 times the size of India. So it will be, again, out of the picture. It could be part of the solution, but it can't be the full solution. So a lot of the hope is in hydrogen. And there's multiple ways. People want to burn hydrogen in their engines. People want to use fuel cells as hydrogen to power the hydrogen planes. And Airbus, which is one of the I guess together with Boeing, the biggest manufacturer of planes in the world, they have committed to have hydrogen planes by 2035, which now they are thinking of postponing a little bit this, which makes sense because it's quite an ambitious target. I mean, those of you working on composites or working in aviation, you know that you develop a small component in a composite, you see that you can replace maybe aluminum by that composite, you can save some weight, and then the industry still takes 20 years of tests before they incorporate this little component into the plane. So developing from scratch in 10 years a plane that is completely different, that would be a gigantic challenge. Another one is steel making. There's some process of steel making where you can replace them with electrification, but not others. In others, you need to use the hydrogen. And then, yeah, I mean, there's other to be discussed. For example, heating is a big discussion now in the UK, whether you use hydrogen or some other source. We have hydrogen buses in London, but again, this is a discussion. Maybe hydrogen, electric battery hydrogen-driven buses will be enough. The same goes for cars. So it depends a little bit on which kind of problems you're looking at, and some of them will be more competitive than others. But I think there's a clear consensus that if you want to decarbonize 100%, you need hydrogen. If you want to decarbonize 60% of society, maybe you don't need hydrogen. But if you want to decarbonize 100%, then you need hydrogen. And then the moment you need hydrogen, then you may as well, use it for some other things. Because the moment you need to build a hydrogen infrastructure, you're going to have to do that. And all the governments at least in the UK and the EU, they have committed to 100% decarbonization by 2050 or earlier. So we're going to have that hydrogen infrastructure pretty soon. The other aspect is also the large-scale electricity storage. So this was a report that the UK commissioned to the Royal Society, and the Royal Society concluded that the best way of storing by far large-scale electricity, as will happen when you have renewables, a system that depends a lot on renewables, which are very suffering intermittency. So you will be to use solution mine salt caverns where you store the hydrogen there. So again, another piece of infrastructure that we need to start building. And in fact, the Royal Society report concluded that we should build those things as soon as possible. So lots of interest in hydrogen, but as we discussed yesterday, hydrogen has a problem. It makes metals very brittle. It's something that we know since almost 150 years ago. And it's quite an extraordinary phenomenon. It's something that is quite remarkable. We showed yesterday this plot, so there's a reduction in ductility that is very significant. You see how the failure strength is dropping by half, just by exposing your sample to some hydrogen gas. We also discussed yesterday the reduction in toughness. This is data I didn't show yesterday, so this is for, I think it's a pipeline steel, yeah, X52 pipeline steel. You can see how the fracture toughness is decreasing as you increase your hydrogen pressure. And what is interesting is that, some aspects that I didn't have time to discuss yesterday is that the susceptibility to hydrogen embrittlement increases with the material strength. So this is for a pressure vessel steel, this is for a pipeline steel, pipeline steel, pressure vessel steel. This is the fatigue. Again, all of this was discussed yesterday, so the effects that you see is fracture toughness being reduced with hydrogen content. You can see it here for the pressure vessel steel. An order of magnitude reduction with just 6 parts per million of hydrogen, and that leads to an order of magnitude increase in fatigue crack growth rate. So we discussed already that yesterday. What I didn't have to discuss yesterday, is that the susceptibility to hydrogen embrittlement increases with the material strength. So these are all medium to low strength steels, but if you go to very high strength steels, you see an increased susceptibility. You can see, for example, here the fracture toughness for a given hydrogen environment. This is like a seawater kind of environment. You can see how for very high strength materials, your hydrogen fracture toughness is below 10 megapascals per square meter. I think it's 7 or something like this what they measure there. So really as brittle as a ceramic. So this is quite important because what this picture is telling us, first of all, is that decades of metallurgical research are being compromised by hydrogen. We are developing very high performance materials, but we cannot use them because they become super brittle in the presence of hydrogen. And the other aspect that this picture is telling us is that with the use of high strength materials, we're going to see more than high strength steels. We're going to see hydrogen system failures in many applications and sectors where we never heard about this problem before, because they're more susceptible. So just a small amount of hydrogen is going to cause those hydrogen system fractures. And that's a problem because hydrogen embrittlement was traditionally an issue related to very aggressive environments. For example, those typical of offshore engineering. I mentioned yesterday these Thunder Horde accidents. That is the biggest accident in terms of environmental consequences in the industry, in the oil and gas industry. But we also see it in offshore wind energy and so on. So this was before these modern high-strength steels came along. So we have the situation where you have a lot of hydrogen coming from those corrosive environments. You have, for example, H2S environments in oil and gas. H2S is kind of a poison. So we discussed yesterday some hydrogen coming in from these electrochemical reactions. So the poison will slow down some of those reactions, favoring the absorption of hydrogen to the metal. So in very aggressive environments, this has been a problem forever, and people, most of the efforts in the community were funded by oil and gas. However, now with these modern steels, we want to use these modern steels everywhere, of course, these high-strength materials, because they are cost-effective. You can use much less material, they're lightweight. So we want to use them everywhere, but this is triggering numerous hydrogen embrittlement problems. I showed you this newspaper article. Yeah.
So this effect of hydrogen, is it limited to steel alone or any metals?
All metals will, there's different effects. So for example, if you're looking at titanium or zirconium alloys, you'll form hydrates, so it's a different type of phenomenon. The susceptibility of metals can change quite dramatically. Some are very susceptible, others less, but they're all susceptible to hydrogen embrittlement. Yeah.
Aluminum also?
Yes. So aluminum is a very interesting one because hydrogen uptake in aluminum is, for example, if you have a hydrogen gas, aluminum will form an oxide and it will complicate hydrogen uptake. But sometimes you can get hydrogen into aluminum just from the humidity. Some people do tests on aluminum, they will put it they won't charge on an electrochemical cell. They will put it in a slightly humid lab and then they'll have enough hydrogen to do their test later on. So it's a big issue for aviation, for example. Some of the aluminum alloys and so on is quite a big issue. So aluminum is a special one, but all of them suffer from embrittlement. Yeah. And this is a problem, because we want to use them everywhere. So, and hydrogen is everywhere, as I said yesterday. So you could have hydrogen coming in from the humidity. You could have hydrogen coming in from your manufacturing processes, from welding. So it was quite common to see, particularly some years ago, lots of people from the automotive industry, Volkswagen, Mercedes and so on, BMW, coming to our academic hydrogen conference because they want to use these high-strength steels just to reduce the weight of the car. But they were, during the manufacturing process, they were getting hydrogen, a little hydrogen into their high-strength steels, and because they were so susceptible, they're seeing embrittlement failures. So that's a problem. It basically has expanded a problem that was limited to oil and gas to many applications and sectors, everything you can think of. There's examples in aviation, in buildings, in cars, everywhere. Again, we are learning things. So initially we just, we came up with these new steels and we said, oh, let's use them. And then we saw, okay, hydrogen causes issues. There was a very interesting case on the metro in the UK, but since this is being recorded, I'll tell you later when it's not recorded, because it was a very interesting case about, and people may think twice about taking the metro in London, because there's some cracks appearing due to probably hydrogen embrittlement. So this is happening everywhere now because of these more susceptible high-strength materials. And of course, this is an issue for the future hydrogen energy. So we need to build this hydrogen infrastructure. I showed you yesterday this image of the Telegraph. These are the two most famous newspapers in the UK. So this is talking about putting hydrogen gas in 2025. This was in 2023. Now they changed. Maybe it's next year. And again, there's big investment for hydrogen. So hydrogen is one of the big 10 points of the decarbonization plan of the UK government and also of the EU. So again, this is kind of a problem. As I showed you yesterday as well, we are already starting to see some hydrogen embrittlement accidents, and the technology is not even there. Very few countries have started to deploy this technology. So that's a problem. And what I want to discuss maybe a bit more today is why this is a problem, or why 150 years after that Johnson's paper that I showed you before, we still don't know much. Still, this problem is not fully understood. We don't have good solutions, and we still don't know very well when hydrogen is going to happen. And I think the issue is that it's a very interdisciplinary problem. So it crosses the boundaries of mechanics, chemistry, material science, condensed matter physics. It's also a very complicated problem because hydrogen interacts with metals in many different ways and on many different scales. It will change at atomic level. It will reduce the bonding strength between metal atoms. At the mesoscale level, it will change the dislocation mobility. So it's many things happening. It stabilizes vacancies. There's many things happening, and I think as an academic, you're going to spend your entire life looking at each of these things and publish many papers and learn a lot about this interesting physics. I guess as an engineer, one has to take a step back and think, okay, it's impossible for us to model each of these phenomena. You will need, atomistic simulations, and we cannot do atomistic simulations of pipelines. So one has to think, okay, what are first-order effects and what are second-order effects here? And that's a complicated discussion, You need to think of clever experiments to figure out what are the first order effects, and every person has a different opinion. And I changed my opinion a few times already over what are first order effects and second order effects in the view of new experimental evidence. So I think this is what makes this problem quite complicated. We do know a few things, of course. You have hydrogen uptake. We discussed yesterday hydrogen uptake can come from multiple sources. You can have molecules of hydrogen gas that dissociate, and then you have hydrogen atoms coming in. You could have hydrogen coming from electrochemical environments. And once the hydrogen atom is inside of the material, then it doesn't know where it came from, right? It behaves in the same way. But of course, you may have different amounts of hydrogen atoms coming in depending on which environment you're exposing your sample to. Then they do, those hydrogen atoms propagate relatively fast through the crystal lattice, and they're attracted to areas of high hydrostatic stress, so they're attracted to areas near cracks, tips, and so on. And that's where a lot of the interesting thing happens. So you might wonder, okay, if this is such a big problem for scientists, what is industry doing? And I have what I think is an interesting example that is related to not exactly the problem that I was discussing yesterday, so it's not really the most common form of hydrogen embrittlement, but it's something called high temperature hydrogen attack. So yesterday, all that I talked about was all room temperature. And room temperature is the worst condition for hydrogen embrittlement. But hydrogen has also some interesting effects at low temperature and high temperature, and we also don't understand those effects very well. So there's something called high temperature attack that occurs in carbon steel typically, and it's a big problem for the petrochemical industry. So I guess the question here is, given how little we know about hydrogen, what is industry doing? How are the industry managing, right? We are not going to sit back and not do anything related to hydrogen just because we don't understand the phenomena. We need to somehow get away, do something about it. So here what they do is what they call the Nelson curve, which is what you see there. So the petrochemical industry will store hydrogen at a given temperature and pressure. And they have these Nelson curves. This is for 10,000 hours for carbon steels. So if you are operating at a temperature and pressure that is below this red line, this black line, you are in a safe operating regime. If you are above, then you are in a safe operating region. And you may wonder how is industry actually creating those lines? Because if we don't know anything about hydrogen, how does industry decide that this is a safe condition and this is not a safe condition? So the way industry builds these graphs is by keeping track of accidents. So for example, this one in the Tesoro and Cortez refinery in the US, 5 people died when they had I think it was a heat exchanger or a boiler. I think it was a boiler. A boiler exploded at a given pressure and temperature. So then the American Petroleum Institute meets and says, oh, well, some people died. Let's do a new line. So this is kind of the approach. It's very much driven by empiricism. And of course, and these lines, these Nelson curves have been going down for the past 30 years, so that's a problem, of course. And of course, this is for a given material, because this is, as you say, this is a problem, this high temperature hydrogen attack is a problem that occurs over very long time periods. So we cannot do experiments because no one wants to run an experiment for decades. So then, it is what it is, so we need to build this information based on accidents, and this is a challenge, not only because we don't know very well what's going to happen, but also, eventually by experience, we eventually will come up with the right curve. But this is for a given material. What if we want to do with a different material? Again, we have no idea who's going to be the brave person to try their luck with a new material. So this is the challenge. So this is what the gap that we're trying to fill. If we have some mechanistic understanding of what's happened, if we have some models that we can physically trust, at least we can provide a good estimate where to start with. You can apply a safety factor if there's some uncertainty carried out in the model. Another example is, for example, this nuclear power plant in Japan. This is a steam generator, and you can see that it's huge. You can see some people here and there. So this is like a 5-story building. It's really gigantic. And because of the hydrogen, they think that they may have hydrogen during the welding process in the weld. Every 2 years, they dismount this gigantic piece of equipment, this 5-story building, and they look for cracks. And they have no idea how much hydrogen they have in there, if they need to inspect every 2 years, every 20, whether that hydrogen is going to cause any issues, but it's nuclear, so they're going to be on the safety side. So yeah, there's a lot of uncertainties and a lot to win if we can understand when hydrogen-assisted failures will happen. This is the example that I showed you yesterday about the San Francisco Bay Bridge, $45 million repairment cost, and the Kashagan oil rig, $3.6 billion US repairing this, just because some pipelines started to crack due to hydrogen embrittlement. They didn't know what to do. They decided to replace all the pipelines because they had no idea about is this a one-off situation? Is it occurring for this particular pipe, for this particular more aggressive environment, or should we just replace all the pipes for the entire oil rig? And they say, okay, let's replace all the pipes for the entire oil rig. So lack of understanding of scientific understanding comes at a cost, at an engineering cost. So this is what we're hoping to achieve.
Just a side note, so when they replace the pipes, are they willing to donate the old pipes to academics to study?
I don't know what they did with the old pipes.
That would be like
Hopefully.
a wealth of material that,
Yes. I don't know what happened with this one in that case. This was in 2014, so 10 years ago or more. I don't know what happened with this one, but that will be interesting. Yes. I know BP has donated some pipes of things that they look. So I don't know who was handling this. I think it was Aramco, the Saudi Arabian. So I don't know what they did with that. So of course that's going to be a problem. And so when we try to tackle this problem is, as I explained yesterday, to try to look into each of the phenomena and try to resolve the physics of the problem to come up with models that are as mechanistic as possible. And how mechanistic we can be will depend on how difficult the problem is, at what scale things matter, how many physics we need to resolve, and so forth. But I'll just say a few words about elaborating on what I said yesterday. I will not repeat myself. So first stage is of course calculating how much hydrogen enters the metal, and hydrogen can come from many environments. But the two that we normally care about is the gaseous one and the aqueous electrolyte one. So we want to resolve those two. We want to calculate how much hydrogen enters the metal. I told you yesterday very briefly that you have something called Siebert's law that you can derive. You can see the derivation here. I didn't have time to discuss that yesterday. So it's very simple. You know that at the end of times, thermodynamic equilibrium will always hold. Whether this happens very fast or very slow is up for debate and will depend on your system. But at the end of times, your chemical potential will always be the same. So if you consider that you have inside the bulk material chemical potential hydrogen atoms, and then in the environment you have hydrogen molecule, then you have to put the 1/2. You have 2 hydrogen atoms in a molecule. We know what is the definition of the chemical potentials for both cases, so we can equate them. This is the lattice one, and then when you equate them, you end up with something like this. Basically, this is the chemical potential. You can make it a function of concentration, and you end up with something like this. So you can see this derivation where you get this fugacity, which is very similar to the pressure for low pressures, if not the same. And there's an equation called the Abel-Nobel equation that allows you to correlate fugacity and pressure for high pressure. So that's fine. This is the indication of the environment. But what you carry over is that because the chemical potential of the environment depends on the hydrostatic stress, this is basically an indication that when you expand your lattice, there's more space for the hydrogen to fit in. So because this is the case, you carry that over and you figure out that eventually you have this term here that is an exponential term where you have a hydrostatic stress. And this is what I emphasized yesterday. An exponential term depends on the numbers inside, but an exponential term can grow pretty fast. So if you have a hydrostatic stress ahead of a crack, this is going to be quite important. So there's a solubility term that I'll explain to you in a minute how we measure that. There's a solubility term, and then there's this term which is partial molar volume, which we know gas constant and temperature. But this term is going to be big, so the coupling with mechanics is important, and sometimes chemists don't realize of this, and it's quite important. But otherwise, it's a closed form expression. You can see the derivation here. Careful thing, one thing that I didn't discuss yesterday, this is for a steady state. So some of the solutions that people are thinking, for example, is what if there has been some observations that when they do fatigue tests in hydrogen gas, if they have leaks, if they have small impurities, for example, oxygen, the embrittlement is kind of suppressed. So then people say, oh wow, then that's a good idea. I have my pipes. I can put a little bit of oxygen. Maybe oxygen can be, it can lead to combustions and explosions and so on. Maybe another impurity. I can add some impurity. That impurity, oxygen or whatever, will compete with the hydrogen atoms for the absorption sites in the surface and will prevent hydrogen to come in. This is, for example, the Japanese are quite strong on this idea. So this is something that you cannot measure at steady state, because at the steady state, your concentration of hydrogen in the metal will always be in equilibrium with the concentration of this surface phenomena washes out. However, we also have transient models. I'll discuss that later. We didn't discuss it yesterday, but we also have transient models where we can test these kind of ideas. But anyway, this is the good news at steady state. Okay, how do we measure these properties? So again, this is something I didn't discuss yesterday, but I thought I should expand. So the solubility of the material is something that you measure through a permeation test. So you have a piece of metal, a membrane, you expose it to a hydrogen-containing environment on one side, and you measure the flux of hydrogen on the other side. So if this is the hydrogen occupancy, you start with 1, and then as a function of time, you see that eventually you get a flux of hydrogen coming on the other side. Because here has no hydrogen, so you have an environment where you have no hydrogen, so you have a flux of hydrogen coming out. That's the idea. Eventually you start like this, and eventually you end up in something like this. So this is a very simple test. You have a membrane, you generate hydrogen on one side, you measure the hydrogen coming out through the other side. This is what we call a permeation test. And you can do it with electrochemical means or with gas. So you could generate hydrogen gas on one side and measure flux with a mass spec, for example, a spectrometer on the other side, or you can do electrochemical permeation. You generate hydrogen in an electrochemical way, and then you measure on the other side. And both should give you the same answers. I think there's a bit of noise related to electropermeation. We'll discuss that later. It's a complicated test. But the gaseous also has its own issues. You can generate oxides. And I think the main advantage of the gaseous system is that it allows you to go to very high temperatures. Because diffusivity can change. I'll put some numbers there so you can see the difference between materials. But it can change quite significantly between materials. So, for example, if I have something that is this size, a very small membrane of a ferritic steel, like a pipeline steel, it will take, in a few minutes, well, not a few minutes, but maybe 1 hour, I can do my test. I can see the flux of hydrogen coming on the other side. If I have something like this of an austenitic steel, I need to wait a month. So the difference can be quite significant. So this means that a lot of people say, okay, maybe we can do membranes that are very, very slow, very, very small, very, very thin, and then I can reduce the time of my experiment. I don't want to be waiting for a month. But you need to be sure that what you're measuring is bulk properties. There's a lot of surface phenomena. So if your bulk is too thin, then surface phenomena can play a role. So it's a very difficult balance. And gaseous systems allow you to increase the temperature. So if you don't care that much about the temperature, we know that all, diffusivity, solubility, all those things follow an Arrhenius law. You could increase your temperature accordingly, and then diffusivity, because it follows an Arrhenius law, it's an exponential, temperature will go very fast, so then you can do the experiment faster. That's the main advantage. But at the end of the day, whether you do it in one way or another, at the end of the day, what you want to measure is the solubility. And solubility is basically the ratio between permeability and diffusivity. And permeability is something that you measure at steady state. So that's good, because that means that we have a more precise estimate. Steady state is a bit less scatter in the data. But diffusivity is a transient prediction. And there's a more scatter in more noise in the experimental data when you're looking at transient problems, which means that solubility is going to be affected by the diffusivity measurement. So there's a bit of a scatter in the solubility, but it's not too bad. And at the end of the day, you care about orders of magnitude in these kind of problems anyway. But that's the point I wanted to make. And then the other aspect, so the two ingredients that you have, of course, the first one is the three ingredients. The first one comes from a finite element simulation. You know your stress-strain behavior of your material, Young's modulus, Poisson ratio, yield stress, strain hardening exponent. You run a finite element, you get hydrostatic stress. This guy is known. There's an experiment, the latency test, that you can measure that, but it has been done many years ago. And it's the same, it depends on the crystal lattice, so we know it already. Temperature, gas constant. Then you measure solubility with a permeation test. And then the fugacity, this is the Abel-Nobel equation for when you're dealing with very high pressures, for intermediate or low pressure system of the pressure. And then the other thing you need to consider is the gas mixtures. So very often in many of these hydrogen energy applications, people are not thinking of using pure hydrogen gas. They're thinking, let's start with a hydrogen mixture. Maybe I'm going to transport natural gas with a bit of hydrogen. In that case, basically, you just need to multiply by the molar fraction of hydrogen in the mixture. So it's still very straightforward. The other case is the aqueous electrolyte case. And as I said yesterday, this is a much more complicated case. So I guess this is good news for the energy transition, because we're dealing with a more simpler case. It's bad news for those people trying to predict, hydrogen embrittlement in aqueous electrolytes, like offshore engineering. So at the end of the day, what you want is here. You want to predict, the embrittlement. This is what you want: a cracking stress intensity factor, a DADT, crack growth, stage 2. But what you really need to resolve is this. And there's two things. You have the hydrogen evolution reactions, and this is something that has attracted the attention of many, many people, because people working on the hydrogen production community, where they're looking at, efficient electrolyzers, they need to resolve those hydrogen evolution reactions. So that is the Tafel, Bohr-Mill, and Horowitzky reactions. And then the absorption reaction. And one has to be careful here, because actually hydrogen doesn't want to enter the metal. The problem is that with very little hydrogen inside my metal, I see embrittlement. That's the fascinating thing about hydrogen. The tiny amounts of hydrogen can really cause dramatic changes in properties. But hydrogen actually doesn't want to enter the metal. Hydrogen wants to recombine into a molecule and run away. So you need to resolve this. In fact, when we do this kind of test in the lab, we normally use a poison to kind of increase the amount, slow down the recombination reaction and increase the amount of hydrogen that comes in. So hydrogen doesn't want to come in your metal, but somehow a little bit comes in and a little bit is problematic. And then the other thing is that, of course, what happens here is here, and this depends on the electrochemical behavior of the electrolyte, and that's going to be very different inside of the some sort of occluded electrochemistry, occluded geometry, than the bulk. But as we discussed yesterday, you know what's happening in there. So you have the Bohr-Tafel-Horowitzky reaction and absorption. So some sort of cathodic reactions plus anodic reactions, the corrosion system. So you can implement your system. These are the equations. These are for acid and non-acidic electrolytes. All those reactions depend on surface reaction rates. And I think I should clarify here that we are always aiming for models that rely purely on material properties that we can measure. And this is the right way to go. And we can do this. This is all reaction rates that we can measure. But measuring these reaction rates is not as straightforward because you need to isolate each of those reactions. So you need to push the system to a place where Tafel is dominating or Bolmer Harabisk is dominating, and then you can measure the reaction rate of each of those. And the other thing is that they're very surface dependent. So you may gain material properties that will relate to a smooth, polished surface, but then maybe in an engineering application that will change. So that's an issue. But basically the reaction rates look like this. I didn't put them yesterday, but I think the key point to emphasize is not for you to learn all this math, but if you think, for example, the Bolmer here, what is dependent on this? The pH, this is the pH. This is going to be given by the electrochemical calculation. The reaction rate by an experiment, this is a material property. Absorption, this is given by, this is the occupancy of the surface by the calculations. And then all this over potential, temperature, gas constant for ice, everything is known. This guy, the over potential, is given by the electrochemical simulation, the same as the pH. It changes in space. And then you have basically a reaction rate. So everything is known. This is the way to go. But again, it's not free of challenges because there's not such a thing as a free lunch, they say, right? Because there's always this reaction rates determined, and there's some tricky aspects of it. And we're doing some experiments to do that. But this is the model that I showed you yesterday. Again, just to emphasize, we finally have enough computer power to solve all the physics that are involved in these things. We know the physics quite well. We need to think of their couplings, of course, but we know the physics quite well. The electrochemistry community knows very well how to describe the electrochemistry of electrolytes. We know quite well how to describe material deformation, hydrogen transport. The challenge is the computational cost. So each of these has nodal degrees of freedom. So depending on your, the battery people, they talk about one ionic species, lithium. Here you have many ionic species. Plus electric potential, plus the surface coverage, plus displacement, hydrogen concentration, fracture if you want. So this is how it looks like. So first you look at the reaction rate, so you have some sort of balance, forward or backward reaction balance in the surface. So those are the Bolmer, Tafel, and absorption reactions. This is what you solve for in the electrolyte. So you have basically the Nernst-Planck equation. I didn't have time to discuss it yesterday, but you have basically changes over time of your ionic species. You have transport due to fluid flow, so there's a fluid velocity in there. There's diffusion. There's electrical potential driven migration, so electromigration here, and there's some volume reactions. And then you have the electron neutrality, which is fine, above a certain number of nanometers. And then this is the expression you solve for the over potential. So you solve here for corrosion and water ionization, whatever reactions are relevant to your problem. And then this is what you solve on the deformation side of things, so hydrogen trapping and transport, and also, of course, the balance of linear momentum. And this representative result I showed you yesterday. So for a given applied potential, with these models, you can predict the evolution of pH of electrolyte inside of the electrolyte. And I'm plotting here, pH, but I could plot any other ionic species, and then the absorption of hydrogen as a function of time. And this is for yesterday I only showed you one representative result, but of course you can change applied potential. You can see how the pH and the hydrogen uptake changes quite dramatically. You can see here from here to there, and so on and so forth. This is for a given different applied potential. You can change the applied potential. You can play with anything you want. And when you look at the crack tip, basically you get, as a function of the applied potential, so for any environment that you care about, you get the hydrogen concentration. This is the orange line. And you can see that we go from cathodic regimes, where you get very high hydrogen uptake, to some sort of valley, and then we go up again for very high anodic applied potentials. And it's very difficult to measure hydrogen uptake ahead of cracks, so it's very difficult for us to see whether this fits the experiments or not. There's some barnacle cell tests that people are doing and some local electrodes that people are using, and they seem to agree. But you can see that it also agrees with embrittlement predictions. So this is for two high-strength steels, iron, met, and ferrium. This is applied potential versus cracking threshold. And you can see that for very low applied potentials, the fracture toughness is the lowest. The susceptibility is the highest. We have a lot of hydrogen, and therefore we have very low susceptibility. Then we go to this peak that corresponds to this valley. So we have very little hydrogen, and we seem to have much higher hydrogen here. I mean, it's a different material, different system, but the qualitative trends are the same. And then eventually, when you go to the anodic regime, you have much more hydrogen uptake, and again, you bring your toughness down. So, qualitatively things seem to be able to match with what we see in experiments. And You can also use these models to gain insight. So this model that we developed is now used also by the hydrogen production community to understand a little bit more regimes of dominance of the hydrogen evolution reaction. And you can see here how different reactions change and become dominant over certain regimes. So you can gain some fundamental insight. And something that I want to emphasize that I told you yesterday, the beauty of these models, as you can, I can decide for a given environment what is my hydrogen concentration in the crack tip. I can then go back to the Siebert's law and determine what is the equivalent pressure, and what is the equivalent hydrogen gas environment that will be equivalent to the test that I'm doing in my lab in a cheap and efficient way. So I think that's quite important because there's a lot of historical data obtained with electrochemical measurements. And the last thing I want to say about uptake is, and that I didn't have time to say yesterday, is that this kind of electrochemical model can also be particularized for the gaseous case for the transient problem. So in that case, you can think of only having a TOEFL and an absorption reaction, and then you have forward and backward TOEFL reactions depending on reaction rates. And you can see that if you particularize this model to steady state, you end up in something like this, that is basically, this is the solubility of your material. So if you recover, basically everything seems consistent, you recover that steady state scenario. But I guess the key point is that Siebert's law works very well for a steady state, but if we want to try this idea of the Japanese of putting oxygen and seeing whether it blocks hydrogen uptake, you need a transient model. This kind of model will be able to capture that. Okay, hydrogen diffusion and trapping. We discussed this yesterday already, just to provide a few extra details. So how hydrogen diffuses is based on Fick's law, and standard version of Fick's law. This applies to many other things. Lithium-ion transporting batteries is also like this. So it's basically concentration as a function of time. It's driven by gradients of concentration. At the end of the day, you want to have a uniform concentration everywhere. D is the diffusivity of your material. And then again, there's a coupling with the mechanics here. So this is diffusivity, concentration, RT, gas constant, temperature, partial molar volume, and hydrostatic stress. And if you take the steady state scenario, so you make the flux equal to 0, you derive this thing, and you can see that C0 is the hydrogen in the environment. Your hydrogen distribution will be basically an exponential term that has a hydrostatic stress. So again, a very strong dependency on mechanics. But what I want to say, I didn't have to say time to say yesterday, is how you measure those things. So basically, you need to measure the diffusivity. And as I said before, this comes from a transient permeation test. So there's a bit of a scatter. And there's a bit of scatter in the test itself. So here on the right, you see these are experiments done in our lab, but they're actually they're supposed to be identical, all of this. As you can see, they're not. And I mean, I shouldn't be the one saying this, but it's not our fault. I'm pretty sure, when you look at the literature, you find even more scatter than what we're reporting here. So these are 13 replicate experiments. You see permeation, current density versus time. And you can see that there's very significant scatter. And there's many reasons why you can bring a scatter into an electrochemical permeation experiment. It's a very complicated experiment. And again, it's in agreement with what it's actually showing less scatter than what most people do. So we were very, very careful in, making sure that the samples had always same polishing conditions. And we're really very, very careful in each of the steps to make sure that we have as repeatable as possible conditions. And still, you get this kind of scatter. In the literature, if you look at other groups, you'll see even much more scatter. But anyway, from this kind of data, you need to get so that's why when we talk about diffusivity in metals, we talk about big numbers. We talk about orders of magnitude. We say this is 10 to the minus 14, this is 10 to the minus 12. But whether it's 1 to the minus 12 or 9, that we don't know. But basically, you have an equation like this. L is the thickness of the membrane. So this is the same permeation experiment that I discussed before. T is time, and N depends on your method. For the breakthrough method is 6, and T becomes the breakthrough time. That is when this current is 0.1 of the steady state current. And then the lag time method, these are the most widely used techniques. All these tests are all standardized. M is 15.3, and T is the lag time, which is basically when the permeation current is 0.63 times the steady state current. So it's okay, but there's comes with a lot of scatter in there. What we have proposed in our group is to use a different technique that is called the isothermal TDS test. So the TDS is the one that I mentioned yesterday, where we measure the trap binding energies by increasing temperature. So it's a very expensive piece of equipment. So it's an alternative for those that haven't. I mean, very expensive. A new one will be on the order of €500,000. So there are more expensive things out there, but it's not a cheap one by any means. So it's for people who have it. But if you happen to have one of those, we find them to be more reliable than permeation. The idea is the same test that I discussed to you the other day. So we increase the temperature to measure the trap density. Here we don't do that. We call it isothermal TDS. You charge a hydrogen sample, you let your hydrogen desorb, you can see here, and then you basically feed with Fick's law your desorption. I mean, this is no load, so this goes away. So the only parameter that can fit here is the diffusivity. So that gives you a diffusivity value. And this is an expression. You can see the desorption rate versus time. This is the experimental and the finite element fit. So this is what you get at the end of the day. This is diffusivity for pure iron. We did many measurements. And you can see here the scatter in the permeation measurements. We measure with both breakthrough and lag time. So this is the first transient of permeation. People argue that the second transient is a bit more precise. Again, we're moving all within one order of magnitude, but you can see that the variation is quite significant, 13.6% in the first measurement, 8.6 in the second measurement. Here, this is the isothermal TDS. You can see that the variation is much smaller, there's much more repetibility, and you are predicting values that are quite similar. So that's the benefit of it. So again, with these methods, I think we can improve measurements of diffusivity, but there's a bit of a scatter in there. Whether the scatter matters or not is a different question, right? Because if I think of a pipeline, for example, whether I assume this is pure iron, so this is representative of those pipeline steels, whether I'm here or here, this means that my steady state of hydrogen concentration in a pipeline will be achieved in 2 days or 2 days and 10 hours. So for an engineer, that's not a very big deal. For other things, it might matter more. For example, if you think of fatigue, when you're doing fatigue loading, what matters is the ratio between the loading frequency and the time that it takes for hydrogen to move within that cycle. So that's governed by diffusivity. So there, you may want to be a bit more precise. But it's true that in many engineering applications, the right order of magnitude is enough for us. And yeah, again, this I showed yesterday. Once you have basically that implemented into your model, you can predict the diffusivity and transport of hydrogen within your component. And you can see here that where hydrogen accumulates seems to agree with what you see in the photographs. And how you practically do it in practice. So if you want to do it in COMSOL, I would recommend that you take a look at these papers that we just published. So this paper that we published recently shows in COMSOL how to implement all the hydrogen transport phenomena. So I'm not discussing, there's other things. These locations can transport hydrogen. There's many other things that are happening. All of those things we implemented in there. So if you are interested in the hydrogen transport phenomena, all of those are implemented in this paper. That's for COMSOL. And then for Abacus, we use a UMAT HT subroutine that you can find in my website. But the idea is to use an analogy with heat transfer. Again, the heat transfer equation is very similar to kind of this Fick law type of equation. So C becomes the temperature, and you can define this kind of behavior with this UMAT HT subroutine. So you can also have all the trapping conditions and all these things implemented there. So in case you're interested, you can download them from there. Okay, the other aspect is the traps that we discussed very briefly yesterday. So the hydrogen not only travels freely through the crystal lattice, it's also sequestered are microstructural defects, grain boundaries, you see here, carbides, dislocations. So this is the trap kind of energy landscape. So this is the hydrogen atoms. I mean, they're jumping everywhere. What we care is about the frequency of which they tend to jump to one place or the other. Here is the activation energy for lattice transport. So this is a lattice spot to another lattice spot, the price you pay to do that. This is the trap energy, and this is the detrapping energy. How do you take the hydrogen atom out of the detrap? That's the idea. And some people take this one to be equal to this one. I mean, it's up to you. But then what we measure here is the binding energy, which is the difference between this detrap and trapping densities. And this is what I showed you yesterday. If you assume what we call Oriani's equilibrium, you assume that the lattice and the traps are in equilibrium, which seems to be valid over sensible timescales, then you can plot a relationship between the lattice. So if I'm not showing it here, but normally we define two concentrations of hydrogen, the one in the lattice and the one in traps, and they are equal to their occupancies multiplied by their densities. So this is the trap density, how many traps you have per unit volume, and this is the occupancy, which goes from 0 to 1. And this is the number of lattice sites, again, density, multiplied by the occupancy, we are from 0 to 1. So these two are in equilibrium, so I can substitute this one here, and I can plot lattice versus binding energy versus trap occupancy. And when I do that, you see this complicated picture that we discussed yesterday. So that's one of the key problems for hydrogen material interactions. Things are very, very sensitive over a small regime, right? So if I take 1 ppm, you can see here from minus 40 kilojoules per mole to minus 20 something. In 20 kilojoules per mole, you go from fully empty, blue color, to completely full trap in yellow color. So that's one of the challenges. So how we determine this guy that is going to tell me where I am? That's the challenge. And as I said, I showed you yesterday this is from a review paper that we published recently. You can see the scatter of the measurements. This is the detrapping energy for various type of defects. The scatter is all over the place. You see precipitate with semi-coherent interfaces go from 20-something to 80. So this will mean fully trapped. This will be empty. Grain boundaries go from 20 to 50-something. So there's a lot of scattering there. And as I mentioned yesterday, this is related to this TDS experiment. And I didn't have time to explain it yesterday, but this is the equipment. This is why it's so expensive. You need ultra-high vacuum conditions. You need a mass spec. And there's multiple configurations, but the one I'm going to discuss is the one of hidden. So you basically have a little sample of hydrogen. You charge with hydrogen. You put it in there, and then you put a heating stage. You ramp up the temperature. So this is the initial condition is hydrogen, full of hydrogen everywhere. Then it's in vacuum, so the boundary conditions are no hydrogen. The hydrogen will leave the sample. And as you increase the temperature, you get something like this, right? So this is the occupancy. You can see it's fully occupied. As you increase the temperature in time, you see that you start losing hydrogen through the sides, and eventually you eliminate all the hydrogen from your sample. And you get something that looks like this, flux or hydrogen desorption rate versus temperature or versus time, and you see some peaks. And here I'm only showing one peak, but some of the experimental data will show more peaks. It will be more. So temperature or time, you have a heating rate, so you're changing your temperature and time, versus some sort of desorption rate or flux, and it will be something like this, maybe. And this means that this was easy to remove. This could be maybe the hydrogen in the lattice, because very little temperature was enough to get the hydrogen out. This required much more temperature, so it was energetically more strongly trapped in my defect, and this was by far the biggest trap. But then you need to go from here, you get this, and then you need to say, okay, how do I correlate this with traps? You have, first of all, you could have multiple traps in one peak, so it's not as simple as just identifying peaks. Second of all, even if you get the binding energy, you still need to think, okay, is this, I got a binding, trap 1 is a binding energy of minus 40. This is what? A dislocation, a grain boundary, a carbide. So you need to be careful. You need to do some metallurgy. For example, you can do, you can change the location densities. You can do a heat treatment, annealing, and see whether those peaks move away. How do they change? You can put more carbides. There's always things that you can do from a metallurgical point of view, and and by experience, we tend to know more or less now which traps are stronger than others. But it's a complicated problem. So for that, we presented this TDS simulator that I showed you yesterday, and I have a nice video. Let's see if it runs, which kind of showcases the issues of this, how it works. I hope you can see it well. So we made a nice video showing the main features of this TDS simulator. It's something we did in MATLAB. It's a very easy to use MATLAB app. And the idea is to reduce the uncertainty, because some of the uncertainty is also related to poor practices in interpreting this TDS data. So you can see that it has a place where you can put the simulation data, so you can pick the models. You can pick the Oriani, Magna Foster, no traps. You put the graphical output, and in seconds, I mean, this is a 1D finite element simulation. It runs quite fast. In seconds, you get the desorption rate versus temperature for the different models. You can plot, hydrogen in the lattice, hydrogen in traps, the combination of both. You can change the units of those things. I don't know if you can play this in a better resolution, because it's not. Let's see if it works a bit better now. Or maybe I'll play something. It will open it full screen. I think it's, I don't know if you can see it. Maybe I'll just play it large. Come on. Is it playing full screen? It's not playing full screen. No? Maybe this is the best we can do. Yeah, so you can see the various options that you have in there. I don't know if it's playing in high resolution. Yeah, so you can play around. You can change, you can zoom in the certain peaks. You can plot flux. You can put desorption, hydrogen distribution. So you can do kind of a 3D plot where you see the hydrogen distribution in your sample, how it's exiting your component as a function of temperature and time. So it gives you various options. It's very straightforward to use. It's an app. The code is available if you want to extend it in other directions, but it's a very simple app. The model parameters are typically the sample thickness, the heating rate, the resting time. So let me go back maybe a few seconds just to show you. So this is the things that you know from your experiment, right? So you pick a sample thickness. That matters because the hydrogen, how fast it diffuses depends on your thickness. Heating rate, how quickly you do the heating rate. Resting time, so this is the time that it takes you from charging your sample to taking it out and putting it inside of the machine. Minimum temperature, maximum temperature. This is numerical input, so basically how you discretize your in terms of number of temperature evaluations and number of elements. And we tell in the paper how many you need. This is fine. what comes by default is fine enough. And then you have your material input. So depending whether you have, and we provide some examples, depending whether you have a ferritic steel, austenitic steel, and so on, you're going to have very different lattice properties. So different lattice activation energy for lattice diffusion, exponential diffusion factor, density, and so on. And then you pick the number of traps, up to 6. Normally we don't have more than 6 traps. And basically you can run your simulation. And then you have, here I pick 2 traps. You can define your binding energy and density of trapping sites, and then you can run simulations until you get a good agreement. So it's very straightforward to use. It's quite fast and it's quite robust. You can see here the effect of the 2 traps. So I change the binding energies and I can see 2 different peaks. And then you can see the effect of the trap 1, trap 2, what is the distribution. So you can plot the whole flux, the whole desorption curve, and see which ones correspond to each trap. And I think and you can take it out and all the usual MATLAB stuff that you can do. So you can do optimization, you can do whatever you want. And I think the feature that I want to go through is the fitting of the experimental setup. So the other approach is this kind of inverse process where you have the experimental data already. So you open up, this is the experimental data points. We know more or less the number of traps. You need to make a guess. You can try multiple fits, or you can give it a lot of traps and then they will find how many traps, because if it finds a trap that is not relevant, it will give you very small trap densities. And then you run this optimization algorithm, which is kind of gradient descent type of method. I think it's a strong particle optimization method. And then eventually you run basically the thing is running many simulations, and eventually it gives you a fitted model, and it gives you all the trapping contributions and the binding energies. So if you have experimental data, you can just let the model run and it will give you the right results. I think that's the takeaway. Let me go back to the slides. So we try to make life easier in the community by providing this tool, and I hope it can be useful to some of you. You see an example here. This is TDS data from a group in NIMS in Japan. I can't remember which material was this, but you can see that we fitted with 4 traps, and you can see very nicely that we capture entire curve, and you can see the model, even this small peak at the end, the fitting tool was able to predict and is able to give you this type of contributions for each trap type. So then you can determine nicely the trap density and binding energies. And I think this, the method people were using is called Kissinger, is not really good because it assumes infinitely fast diffusion, and that's obviously erroneous. We are now writing a paper explaining how big the error is, and it's quite large. Depends on your material and so on, but it's quite large. So I think it's important to move towards these tools, and then hopefully we can reduce this big scatter here. Okay, the other techniques that people do, this is not something I do in my group, but I thought, to make it more instructive, I could tell you a little bit of what other people are doing. One is the secondary ion mass spectroscopy. As far as I've been told, this is quite qualitative. So you see here, the idea or the hope is to see the distribution of a space of hydrogen, and you can see here that they are able to see some hydrogen accumulation near the edge where you have a lot of hydrogen, but it's still very qualitative. We're not yet there when it comes to quantitative predictions. And the other one is atom probe tomography. This is I was told yesterday IIT Madras has an atom probe tomography equipment, which is this is a unique and expensive piece of equipment. Imperial bought one only a few years ago, and it cost 10 million pounds. So it's a special one that has some cryo stage, but still it's a very unique and expensive piece of equipment. But here people are reporting, there's a bit of debate in the community on what you see or you don't see. It's a complicated technique. It takes a long time for students to get data. But once you get the data, it's actually quite exciting because you can see that you get, this is the deuterium, which you can think of it as hydrogen atoms, all these red dots. These are dislocations in blue. This is a grain boundary in red. And you can see how the hydrogen is really accumulating in that grain boundary significantly. So it kind of connects a little bit with the mechanistic discussion that we discussed yesterday, with the Oriani type of trapping equilibrium that we said before. So hydrogen does like to sit on the grain boundaries, and you can see here how they observe this with atom probe tomography. Anyway, whenever you have those trap densities and binding energies, then you need to come up with a model, and the model is very simple. As you say, you have this lattice and trap hydrogen concentrations. You have an effective diffusivity that is going to be reduced by your trapping occupancy, by your traps, and then you can think of it as a thermodynamic, or some people use this McNabb-Foster model where you have more kinetic description. To be honest, I don't see that much difference. I think Oriani holds most of the time. The aspect that I did emphasize yesterday was, again, if you're interested in how much hydrogen you have trapped in these locations, you normally define something like this. This is the lattice parameter, this is the trap density, this is the density of hydrogen trapped in dislocations. And what is important is not only to consider the statistically stored dislocations, which are related to plastic strains, as shown by Taylor, but also the G&Ds, geometrically necessary dislocations, that are related to plastic strain gradients. And these are quite big. You can measure lattice rotations in EBSD, and you can see that they're quite big ahead of cracks and inclusions. And one thing that I discussed yesterday is that G&Ds also bring an elevation in stress. This is something that we see all the time at the macro scale, so micro bending, micro torsion, but also in indentation. Right? In indentation is similar to fracture in that you could be indenting something very big, but your plastic zone is small, so you have big gradients of plastic deformation. This is similar to fracture. In fracture, particularly in hydrogen embrittlement and other quasi-cleavage phenomena where the plastic zone failure happens at very low applied loads, so the plastic zone is small and contains big gradients, you can see that these big gradients are going to lead to stress elevations that are quite significant within microns ahead of the crack tip. So of course here a key question is, when does hydrogen embrittlement fracture happen? Does it occur at microns near the crack tip or at millimeters ahead of the crack tip? Because if it happens at millimeters, then these size effects are not going to be important. But if it happens at microns, they're going to be very important because the hydrogen concentration is going to be very large. And we discussed yesterday after the seminar about mechanisms, and some of the people that do not believe in the cohesion mechanisms, they will argue that it's not possible to achieve the high levels of concentration and stresses that you need to the coherent interface. But I think they were not considering this, and I think this is the key ingredient that you need to consider, because then you see very high hydrogen concentration. You see orders of magnitude change, and also very high stresses. And this is the only way that we can capture what we see in experiments. So this is Sims measurements for different applied loads. Hydrogen concentration, you can see that it becomes very, very large. No way you can achieve that with conventional plasticity, like von Mises. With gradient plasticity models that capture those G&Ds, you do capture this effect. And I mean, and G&Ds exist. We have seen them in the lab every day. We do microscale tests, so those things matter. One last thing I want to say about trapping is that there's been a bit of discussion on whether traps can be used to mitigate hydrogen embrittlement. So some people say, okay, assume that you have a material. In some material systems, it's much more complicated to understand what's happening in the mechanisms. But in others, it's quite clear. For example, in nickel, we have seen both at room temperature and cryogenic temperatures, where all the plasticity hydrogen interactions are precluded, that you get grain boundary decohesion. So I say, okay, this material system we understand quite well, right? We think that hydrogen trapped in those grain boundaries here is the one causing the problems. So what can we do about it? Can we, for example, add a lot of these carbides and preclude the hydrogen accumulating in grain boundaries? If we have a finite amount of hydrogen, then okay, why not? They will be trapped in the carbides and they will not go to the grain boundaries. And this has been shown to work by the petrochemical industry for chromomolybdenovanadium steels. So they used to use chromomolybdenovanadium, but these are applications that are very specific. So they will store hydrogen in pressure vessels for a limited amount of time. They will change the temperature. There will be a cooling and a heating. The hydrogen will leave the component, and it will be distributed within the metal, and it will change the distribution due to the change in temperature. So you did get this distribution of hydrogen within the lattice to traps due to change in temperature. So you will get a hydrogen going to the carbides, and you will see less embrittlement. So it has worked, this idea. But it has worked in what we call a closed system. So that's a system where you have only a little bit of hydrogen circulating around. You don't have hydrogen all over the place. So whether that works in an open system where you have a permanent source of hydrogen, which is the most relevant case for all these hydrogen energy applications, that's a different question. And the group of Petros Sofronis, also Rick Gangloff and so on, they concluded that this couldn't work. They did some diffusion simulations ahead of a crack, and they saw that, first of all, the quantities that you get at a steady state, so they basically plotted stresses ahead of a crack using conventional plasticity, but your material model doesn't really matter that much. You get this hydrogen concentration. Normally, because it depends so much on the tensile stresses, on the hydrostatic stresses, the hydrogen concentration kind of follows your stress distribution. So in conventional plasticity, your hydrogen distribution in a large scale elastoplasticity, your stress concentration looks like this, and therefore your hydrogen concentration also looks like that. And they concluded that the steady state lattice hydrogen concentration, of course, is not dependent on how many traps you have. So adding carbides will not really benefit. And the only thing that will change is how long it took you to get to that point. But they looked at a ferritic material, and in that ferritic material, in minutes, you have a hydrogen concentration that was already 90% of the steady state value. So yes, you can add carbides, and that will delay how quickly you get to this point, but in minutes you're already here. So for an engineering point of view, people said, okay, this is not going to work. This is the idea. If you have a permanent source of hydrogen, you'll get to steady state or close to steady state very, very quickly. And I think what they did was fine. I mean, there's nothing wrong with it. I agree with it. But there's one aspect where it can play a role, and it's fatigue. Because, okay, yes, if you think of a pipeline standing there, then delaying a few minutes things is not going to change much, because the pipeline is going to be there for 50 years. But when you're dealing with fatigue, you have cycles of load, and as you can see here, because the hydrogen is following the lattice hydrogen concentration, because the hydrogen is following the hydrostatic stress, your hydrogen concentration is going up and down. So you have a frequency dependency. This is what you see here. This is the hydrogen concentration, the maximum hydrogen concentration ahead of the crack. So I'm looking at this peak. So I'm looking at that peak. Well, it's actually not the steady state one, but more like this one. I'm looking at that peak. I'm looking at that with finite element. This is a very simple calculation. There's no phase field, just a coupled diffusion deformation simulation. And you can see here that if I change the frequency, or this normalized frequency, basically it's a competition between frequency, some sort of length scale, and your diffusivity. This is the normalized frequency. So if you do that, you see that if you load very, very fast, so the pink line, then there's not enough hydrogen. The hydrogen doesn't have enough time. So basically, what happens in the hydrogen ahead of the crack tip is something like this, right? You start here. Well, let me plot it a bit better. So assume that you have a hydrogen from the environment, that is Cm, and assuming conventional plasticity, at the steady state is going to be something like this. Initially, basically, is this. At t equals 0, there's not enough time for the hydrogen to follow the hydrostatic stress. Eventually, or like this if you have no charge, eventually starts following the hydrostatic stress. So this is at the beginning, a bit later on, and then eventually you get there. So in fatigue, because when you reach a certain point, you start unloading, this goes down again. So it's going up and down, up and down, up and down. So I'm plotting this quantity, the maximum quantity, and you can see here that this is the pink line. So, and this has traps and has the whole package. So this is a multi-trap model. You can see that if I load very slowly, so the black dashed line, my hydrogen concentration becomes quite large, 3 times the environmental one. But if I load very slowly, it becomes 2 times. So there's a bit of margin for improvement. So basically, this is the effective frequency. And this is what we know in fatigue. In fatigue, if we load very slowly, we see much more hydrogen susceptibility than if we load very fast. So this is to be expected. But the key thing is that what matters is this non-dimensional parameter, so the ratio between frequency and diffusivity. So if you can change your traps and change the diffusivity, slow down your diffusivity, then you may be loading at this frequency, but you are somewhere here. This is the point. Because in reality, what matters is the ratio. So even if you're loading at this frequency, if you change your diffusivity, you can go from here to here. So you bring down that peak hydrogen. You don't bring it in a static fracture over the length scale that matter, but you bring it in fatigue. And what we show here in comparison with experiments, we ran some experiments where we saw that it was fatigue experiments, and we saw that if we did experiment at 1 Hz, we didn't see, it was fast enough, we didn't see an embrittlement. The response was the same in air. But when we run experiments at 0.1 Hz and 0.05 Hz, we did see embrittlement. So now what we do is we do a theoretical study where we basically change the diffusivity. We add a number of carbides that is sensible, and we saw how the maximum concentration changes. And we can see that you can bring it down for a frequency of 0.1 Hz where we saw embrittlement. If you add enough carbides, you can bring it down below this threshold where we think embrittlement happens. So the key takeaway is that, okay, this idea is a bit risky and it will not be a solution for everything. But maybe in fatigue it can work, because the time scale that matters is the time scale of the loading cycle versus the time scale of the crack accumulating, the hydrogen accumulating near your crack. And I mean, you're not getting gigantic gains because you can also not put carbides every nanometer, right? There's a limit on what you can do from the metallurgical side of things. But we change the carbides through densities that we think that we can do, and you can increase, let's say, the regimes of safe frequencies by an order of magnitude. Whether that as an engineer matters or not, maybe you are dealing with frequencies that are much lower anyway, and then you don't care. It will have to be a solution very specific to a very specific problem, but it can be a solution. Okay, this is an important slide, so I'm going to spend a bit of time in here. I think it's important to get a taste for the numbers, because materials can change very dramatically. So let me look first at this bottom slide. So let's think, for example, the DL. Let's look at the DL. This is the lattice diffusivity in meters squared divided by second. You can see that ferritic materials like pure iron they have 10 to the minus 8. Austenitic, 10 to the minus 16. So there's 8 degrees of freedom, 8 orders of magnitude change in diffusivity. So this is why I told you before, if you had a membrane this thick, in a few hours I can see the hydrogen on the other side if I have ferritic steel, but it will take me a month to see it in the austenitic steel, just because it's 8 orders of magnitude. So this effect of hydrogen can be very dependent on the material that you're working with, and you can see, ferritic steels is where the hydrogen diffuses the fastest. Somehow susceptibility increases is related to diffusivity. So the most susceptible materials are ferritic steels. The martensitics are also very susceptible. You can see that they have 10 to the minus 12. Nickel is also very susceptible. Nickel alloys, 10 to the minus 13, minus 14. Aluminium is also susceptible, minus 12. Austenitic is minus 16. This is the most resistant hydrogen materials. And it's interesting to look at this as well at the solubility. So this is the solubility of the material, and these are the concentrations for a given exposure pressure, so 30 megapascals hydrogen pressure. So you see the solubility also changes quite dramatically. So in austenitic steels we measure hundreds of ppm of hydrogen. In ferritic steels we measure 0.1 ppm of hydrogen. In nickel we measure tens, maybe 90, 80, depends on your material and so on, but this kind of measurements. So this is also quite important. And what I think is quite interesting as well is that austenitic steels, they can absorb a lot of hydrogen in their lattice, but they are the less susceptible ones. So susceptibility does not correlate with solubility. It's quite the opposite. There's an inverse effect. It correlates with diffusivity. And I think it's good to have some numbers in your head. So okay, what is the diffusivity in these materials, in these other materials, solubility in these materials, and other materials, because it really changes quite dramatically. So I think this is an important takeaway. Yes?
In your previous slide, so you mentioned about traps, which is carbide. Can you please comment about what is the nature of interface? Coherent, semi-coherent, incoherent?
Yeah, this is another question. And a lot of people actually, so it's a good question, a highly debated topic. A lot of people would actually argue that, maybe a carbide is what initiates the entire embrittlement. You see the grain boundary cracking because, grain boundaries are the weakest path. So once you initiated a crack, then the crack will decide to go to the grain boundary. But the cohesion of the carbide, this is actually what drives the entire hydrogen embrittlement process. So it's a big discussion and then of course it matters whether it's semi-coherent, coherent. They also report different binding energies. I think you have it here. So you have precipitates with coherent interfaces, with semi-coherent interfaces, different binding energies. Ideally, what people have tried is in vanadium carbides in chromoleum steel. This is what people have tried. I think there has been something else. I'm trying to remember. Harry Badisia in Cambridge has done quite a lot of work on this, very nice work. I think it has been mostly vanadium, because then they can control them. They can also very nanometer scale. They can then be very small. But all of those things are important. So and a lot of people seem to be very interested in, as an engineer, I must say, I don't know how far you can get with these things. But a lot of people feel very excited about the possibility of developing hydrogen resistant materials, and we don't have a lot of other good options. So they are looking into these things, and again, this matters, whether it's a coherent, semi-coherent interface. And
Another question is that when you talk about trapping characteristics, it depends on the binding energy as well as the hydrostatic component. So when it comes to carbides, so because of the misfit at the interface, which one dominates? Whether it is the binding energy dominates the trapping characteristics of carbides, or the stress?
so you're thinking because you're going to have a raise in stresses, then hydrogen will be attracted to it in addition to being attracted despite being the trapping as well. Yeah, that could happen. I think that the stress goes inside of an exponential term, but what happens inside of an exponential term depends on the numbers that you have in there. So the parts per molar volume is 2,000 meter cubic divided by mole. So it becomes very significant if you have very high stresses, which we normally achieve ahead of crack tips. I don't think the stresses you'll get ahead of a carbide will be that strong. So I think the trapping, my guess, I never look into it very carefully, but my first answer will be that trapping probably dominates in that behavior. Because you can see that the trapping is quite significant. If your binding energy is quite strong, and they seem to have reported some very strong binding energies of 90 kilojoules per mole in some of this, you'll basically have some very significant accumulation. Very little hydrogen in the lattice will drive significant accumulation in your carbide. And the vanadium carbides have worked, so that's, I think, a good indication that for finite amount of hydrogen. not for infinite amount of hydrogen. So I think it's an indication that somehow the trapping is dominant over other phenomena that may happen. Yeah. Then we are dealing with.
You briefly mentioned about the susceptibility versus the solubility. Could you please repeat that?
Yes. So, I mean, we don't fully understand everything, of course, and not always these things correlate one-to-one. You have different scenarios. But in general, we know that the higher the diffusivity of hydrogen in your material, remember, by the way, that solubility, I have it here. Remember the relationship between, what do I have at the beginning was, right? No, I was at the beginning, I think. This is the relationship between solubility, diffusivity, and permeability. So, the higher the diffusivity, the lower your solubility is going to be. I mean, you also have permeability in there, so it's not as simple, but in general, the higher the diffusivity, the lower the solubility. And this is what you see here. But susceptibility typically correlates well with, sorry, I went too fast. So susceptibility typically correlates with diffusivity. Let me take you back to the slide where they have the models. Yeah, so diffusivity normally correlates with susceptibility. So materials where hydrogen diffuses faster, they are more susceptible. And I mean, I don't think there's a clear understanding why necessarily this happens. There could be arguments in the case that because you could do even if you do experiments at very, very, very low strain rates, whereby somehow your diffusivity gets compensated, you are dealing with steady state scenarios. You also see this. What is a steady state at the macro scale might not be, of course, what is a steady state at the micro scale. So that also can matter. But in general, it's not as simple as just saying, oh, hydrogen will move much faster, that you get more hydrogen accumulation, because we also see it at very, very low or constant load experiments and things like this. So I think that's an aspect of discussion, but it is what we observe. So the solubility, because it's typically inverse of diffusivity in a way, so materials have very high diffusivity, have low solubility, seems to be inverse correlations with susceptibility. So ferritic steels are the ones that suffer the biggest hydrogen embrittlement. Those guys have very low susceptibility, very low solubility. There's very little hydrogen that actually they can accommodate. Again, it's more or less a qualitative relationship, but more or less that holds, I would say. Yeah. So nickel alloys can sustain much more hydrogen, and they're quite susceptible as well. High strength nickel alloys and so on, but it's still more or less that's the correlation. Yeah. There's a much bigger, stronger correlation with strength. The higher the strength of your material, the higher the susceptibility. That correlation is quite strong. But for example, austenitic stainless steels, they are by far the best. They have the highest solubility, they have the lowest diffusivity, and they are by far the best when it comes to embrittlement. It's actually not that easy to embrittle an austenitic. I mean, depends on how you define embrittlement. You do see a reduction in area. If you put a crack in it, you see enhanced fatigue growth, but it is not that easy by any means. It's the most. So for aviation applications where they're very worried about safety and cost is not an issue, 316L is what is being considered. Yeah. Okay, so finally we deal with embrittlement stage. I'm not going to repeat all the story I told you about phase field. You already heard it a couple of times, but we use phase field. We have used other methods before. We have used Quististon models. We have used, I think XFEM we did as well at some point. So we use other methods before for hydrogen. Quististon models are not that different. At the end of the day, you have a strength, you have a fracture energy, a toughness, so that's fine. I think the benefit of phase field is that the convergence is much better. It's a much more robust method, but also it allows us to model much more complicated fracture phenomena. With cohesive elements, we're okay to model a mode 1 fracture experiment, but it was not so good if you don't know where your cracks is going, like the examples of the pipes that I'll show you later. So again, just to emphasize the key points: computational robust, physically sound. That's why we like it, and we extended this to phase field fracture, and we discussed yesterday the coupling. So again, phase field degrades your load current capacity, the hydrostatic stress drives hydrogen transport, and there's a reduction in damage with the hydrogen concentration. And this is what we discussed yesterday quite a lot. We said, one way was the empirical way. You do fracture toughness experiments, and based on the fracture toughness experiments, you can feed that data and input into the model, right? If you think, for example, these are pipeline steels, you can think of GC being equivalent to J. J and G are the same units and so on. So you can fit, if you have enough data over the regime that you care about, and normally, most materials exhibit something like this, so they don't go into negative toughnesses or 0. At some point, they will saturate. So if you have enough data points, you can fit those data points. So this is, for example, for pipeline steels, 2 types of pipeline steels. There's a lot of scatter in the data, as you can see, but anyway, assuming you have a good data, here the data is a bit more consistent. You can fit that data with a polynomial, and then you basically say, okay, you are measuring your hydrogen concentration as a function of space in your phase field model. So you can come in here, and then you can reduce quantitatively your fracture toughness. I think that's the kind of engineering approach. And this is what we discussed yesterday. And this, implementing this in your phase field model is straightforward. You have the data, you pick your favorite polynomial to fit that data. That is a function of concentration, so you have this multiplication. You get this concentration here, and you reduce your fracture energy based on this, whatever number comes in there. I think so. That's relatively straightforward, and this is something what industry uses. Of course, the more interesting thing will be to figure out what is the embrittlement mechanism. And if we could figure out what is the embrittlement mechanism, then we will be able to give answers to the problem. And I mean, the good thing is that the model allows for any mechanistic interpretation. This is a point I emphasized yesterday. It's a universal model. I suggested yesterday one embrittlement mechanism that I had in mind. I'll elaborate a bit more on why I think this is the case later on or tomorrow. But the key point is that you can pick anything you want. So any micro or macro mechanical variable that you think is interesting, that drives your... So there's a lot of theories based on plasticity, on dislocation density, or hydrogen trapped in these locations. You can always incorporate all of those theories into this framework, because at the end of the day, this is fracture mechanics. All the mechanisms are either embedded in this graph, or if you want to define them by yourself, as long as you have variables that are resolving the physics of your variable, then you're ready to go. So let me see, how many slides do I have? Okay, let me continue a few more slides. We still have a few minutes. So this is what I said yesterday. Okay, if you want to answer this question, the question is, how does hydrogen make metals brittle? And this is for nickel, but with many other systems, we see something like this. In the absence of hydrogen, you see these microvoids growing and coalescing, so ductile fracture mechanisms. The moment you bring hydrogen to the same material, you see a complete change of fracture surface, very brittle, with hydrogen occurring along the grain boundaries or other interfaces, cleavage-like interfaces. I told you yesterday that the ingredients that I thought were needed to understand this was basically to run atomistic simulations. If you run atomistic simulations, I mean, the atomistic community is still, improving this prediction, so there's still a bit of a scatter among the community. But qualitatively, they all say the same. So hydrogen reduces your atomic bonding strength. How much it reduces, again, I was doing a compilation recently of the atomistic literature, and it's a bit all over the place. So I think, there's issues with the potentials, there's issues, I mean, this is very useful insight, but it's a complicated area. But this is an example, what you see for 2 binding energies in nickel. This is from the group in Centef, and you can see the fractional reduction with the hydrogen occupancy. You can see that it's a significant reduction if you have enough hydrogen occupancy. Some of the people have reduced reductions of 90%. Some of the people have provided reductions of 10%. So it's still, a bit of a discussion, but more or less we think 30, 40, 50% reduction is something that is doable. Then you need to figure out how much hydrogen you have. This is what I mentioned yesterday. So if your interface has very little hydrogen, there must be another mechanism. If your interface is full, maybe a pile-up of these locations, driving hydrogen to your interface. If your hydrogen is full of hydrogen, then this might be enough. And this is what you get. So this is the Oriani equilibrium that I showed you before. And we know, for example, strong traps, such as grain boundaries, we are somewhere here. So remember the hydrogen concentration near the crack was going to be quite high. So it's likely that your interface is going to be pretty full. That's the idea. And this is what we see, by the way, in the APT, right? We see that in the APT that the grain boundaries are actually full of hydrogen. So then the last part is, okay, let's assume that's true. We've seen the APT. You're probably right. Grain boundaries are full of hydrogen. The TDS measurements also suggest that it's a strong trap. Plenty of hydrogen embedded in there. The DFT calculations, there's a bit of scatter, but everyone seems to agree that more or less between, you get between 10 and 90%. So there's some sort of reduction in your bonding strength. So the reason why, so that could explain it. Because we know that, we have a bonding strength between grain boundaries, and our stresses are never big enough to reach their bonding strength. That's why we need these voids to grow and nucleate and coalescence. That's why we get ductile fracture processes. But it could be that eventually if your stresses are big enough, then eventually you get, this kind of mechanism activated before the other. It's a competition. You have voids growing, and at the same time you have stresses near the grain boundary. Normally our stresses are not big enough. These grain boundaries or the lattice strength are very high. 10 times the yield stress, 9 times the yield stress. Our stresses are never that high. So this means that eventually you never reach those yield stress, you need those buoys to grow and so on. So this is the question, If we can trigger the failure of those grain boundaries, then we will switch from ductile to brittle failure. But is this possible given that these grain boundaries have such a high grain boundary strength? I mean, it must be possible because we see it in the experiments. The grain boundary has decohered. But how can we understand this? And if you do a conventional plasticity simulation, this is from Sofronis and McMeekin, some of the oldest papers in this area. McMeekin was the first to run finite element simulations of crack tip stresses ahead of a crack in elastoplasticity and fine strains. So here this dashed line is a hydrostatic stress. So this is the hydrostatic stress. You can see here, the grain boundary strength is 9-10 times the yield stress. The maximum stress that you get ahead of your crack tip is 5 times the yield stress. So we are pretty far away. So this is something that has puzzled the community for quite some time. How can it be that, if things fail, we see this grain boundary open. How did this grain boundary open when we need stresses that are 10 times the yield stress, and our calculations tell that our stresses are 5 times the yield stress? So that's something I'll discuss tomorrow, because we only have 7 minutes left, so not worth opening again a set of slides. But it's a problem that relates not only to hydrogen, but also to many other mechanisms, quasi-cleavage and the low temperatures. Anytime you look at an interface that has broken, you say, how can this possibly be? That interface has a very high strength. Our stresses are not high enough. We see also in metal ceramic interfaces, plenty of plasticity, but still very sharp cleavage type of failures. So there's some discussion related to that. Any questions so far? Okay, if not, we're going to finish 5 minutes before, but I'll see you tomorrow for the second part of this, and then getting into more phase field modeling of other applications, multi-physics modeling. Thank you.